Good morning, everyone. I have to apologize that this is a re-recording of lecture 10 I gave earlier in the morning. So accidentally, the recording was not successful for the live session. So that's why I'm doing the re-recording based on the notes I already wrote. So this might be faster than our regular recorded live seminar, live lecture. So please pause if you think I went too fast. Okay, so I'm just going to repeat what I did in the lecture. First, as a recap of lecture 9, we apply the Fisher scoring method to the GLM for maximizing the log likelihood. So in this specific application, we call Fisher scoring as iteratively reweighted least square, and you will see why we give it the name. In lecture 9, we basically did a very tedious derivation for the score function of the log likelihood of GLM. If we look at here, what we basically did is to obtain the gradient of the log likelihood against each element beta j in the beta parameter. To do that, we use the exponential family log density in this form. Here, the key parameter is theta I, the location parameter, which is connected to our beta. And we apply the calculus chain rule to derive the partial derivative of each element in the log likelihood. So this is what we call lowercase li. It's the log likelihood contribution of observation I. You can think of this as if we only have one observation I, this will be the log likelihood. So we take the partial derivative of Li against beta j. To achieve that, we use the chain rule. We first take differentiation of Li against theta I, the location parameter in exponential family, then d theta I d mu I, which is the expectation of yi. And y mu I is connected to beta j through the linear predictor eta I. So we do d mu I, d eta I, and finally partial eta I, partial beta j. And eta I itself is a linear predictor, which we wrote as xi transpose beta, which is a linear combination of xij times beta j. So therefore, the last part is just xij. So next, after we derive this partial Li, partial beta j in this form, we actually rewrote we write the gradient of L, the log likelihood against beta, which is a p-dimensional vector using a matrix multiplication form. So here we define this vector y minus mu d eta d mu. This is a notation for this vector. Its entries are yi minus mu I times g prime mu I. We also created a diagonal matrix for a weight matrix W, which we'll see why it's a weight. And where each entry is variance yi times g prime mu I squared in the denominator, the inverse of that. That's our W. And also have the jth column of the design matrix X called xj. So together, we can see that the gradient or the partial derivative of log likelihood against beta j can be written as this matrix form, xj transpose w times the vector. Stacking this thing by j, so we get a gradient. That would be just design matrix x transpose w times the vector. That's the score function we have. The next thing we need for Fisher scoring update is the Fisher information, which is the negative expectation of Hessian of log likelihood. So we continue to do another partial derivative of Li against beta k. So by doing so, we get two terms. And luckily, we need to take expectation to get Fisher information. So with expectation, the first term vanishes because expectation of yi equals mu I, we get 0. And this term is not related to random variable yi. So it gets out of expectation. So we have 0 for the first term. And we are left with the second term. And for the second term, luckily, the differentiation will remove yi. So we no longer have a random variable in it. We are just left with a constant. So we can get expectation away. And because partial mu I, partial beta j is something we can easily work with. That is, here we have the link function to go through this step. So after that, applying chain rule again to get from mu I to eta I, then do partial eta I, partial beta k. We can simplify it as just this. We have negative xik wixij. So this is actually the contribution of the ith observation. We need to take the sum over I for I from 1 to m. So we get here. This is the jkth entry in the Hessian of the log likelihood. So I need to put here, it's the second partial derivative. And also here, I forgot to have the 2 here and 2 here. Okay, so I would have this, and I can write this as a matrix form again. So it would be negative the transpose of the jth column of x times w times the kth column. And that's the jkth entry of the Hessian of the negative Fisher information. And then by stacking them together, we can get, okay, the Fisher information matrix, which is actually a P by P matrix. Since P beta is P dimensional, is X transpose WX. Then we can use this Fisher information and the score function we have derived in the update step of Fisher scoring. So this is what we get, okay? This is what we have seen in the end of our last lecture. Then what do? We want to simplify this a little bit. We first multiply x transpose wkx to each term. That gives me this x transpose wkx times beta k plus 1 equals x transpose wkx times beta. And because of cancellation, I have x transpose wk times this vector in the kth iteration. Now you see I have x transpose wk in both the two terms, so I can combine them into here. So I just have x transpose wk times x beta k plus this vector in the kth iteration. So this is the key thing. Now I'm going to call this vector, define it as zk, which is equal to x beta k plus this term. And I give the name as working dependent variable. Note that this is n-dimensional, so we are going to use it as our response, just as in a linear regression in the kth iteration. So using the simplified notation zk, you see that now I'm going to multiply x transpose wkx inverse again to both sides. I can have my update beta k plus 1 equals x transpose wkx inverse x transpose wkzk. This reminds us of the weighted least square we talked about last lecture. So in the weighted least square, you see our MLE or weighted least square estimate has a very similar form. Beta hat equals x transpose wx inverse x transpose wy. Y is the response. Here we replace the response y by zk, our working dependent variable. And furthermore, in the weighted least square, in the weight matrix, each diagonal entry is actually the inverse of the variance of yi, the response variable. So now we have two questions. Do we have a similar interpretation of the weight in this update step? Another question is, what is exactly the working dependent variable zk? So we will address these two questions one by one. What is zk? So let's look at its ith entry for the ith observation. We call it zik. To understand this, let's take a look at its form. Xi transpose beta k plus yi minus mu ik times g prime mu ik. So we know that Xi transpose beta is what we call eta I, the linear predictor. And by the systematic structure of our GLM is G mu I. So if we take differentiation of eta I against mu I, we get G prime mu I. And this actually allows us to do a Taylor expansion for eta I at its current value, eta ik. So the first order Taylor expansion will give me eta I minus eta ik. Suppose the eta I is the true value we're interested in, and eta ik is the current value in our iteration case. Is equal to mu I, the mu I value we are interested in, minus mu ik. We take their difference and use the gradient or first derivative at mu ik as the slope. So this gives me a linear relationship between mu I and eta I. Okay, so we're basically approximating this g function by this linear function. And then I can move this eta ik to the right-hand side, and then I can write, okay, eta I is approximately equal to xi transpose beta k, which is equal to eta ik plus this term. So you see, I'm basically writing eta I as an approximate way using the mu I and the current value of mu ik and the current value of beta k. So if I further use yi to approximate mu I, you see that this term is already very similar to our zik formula, except that here we have mu I, here we have yi. If we consider yi to be an approximation of mu I, right, its mean, we can have this form, which is exactly how we define the working dependent variable. So what this means is that we are trying to convert our yi, which do not directly have a linear relationship with our predictors, by doing this transformation. So we are turning yi into sort of like eta I. And eta I is a linear predictor and is a linear function of the predictors, so that we are trying to create a transformation of yi. So we have a linear regression problem in the case iteration. That's why we call it working dependent variable. So we are turning a general GLM problem into a linear model problem. So if this is our new response in the kth iteration, the next question is, does the weighted least square actually match what we have as weights here? Yes. So by our definition, weighted least square, here the weight needs to be the inverse of the variance of yi. And here our response is zik. So we just check what's the variance of zik. In fact, based on this formula, if we ignore that beta k and mu ik uses our data, we just treat them as some values that are fixed, then the only random variable is yi. So then we see by the variance formula, this is equal to variance of yi times the square of g prime and mu ik. And this is exactly what we have in our definition of wi in our last lecture. So here is it. So here's what we have in the W. You see, this is what we have in W for Wi. It's 1 over variance yi times g prime mu I squared. So it is exactly what we have right here. So therefore, we have the wik just as the inverse of the variance of zik. That makes us exactly in the scenario of weighted least square. Okay, so in summary, what we have is that in the iterative weighted least square, although the iteration is because of Fisher scoring, but when we implement it in our GLM case, what we have is in each iteration, we first construct working dependent variable zk, then we run weighted least square based on the weights for the zk. And why do we call it iterative reweighted least square. The reweighted means that in each iteration, the weights needs to be recomputed. So we have a new set of weights for the new ZK. So here is a concrete illustration of how it works. First, we need some initialization for our parameters. So it's easiest to initialize mu because it is the expectation of y. So for simplicity, we can set the initial value of mu, we call mu 0 just to y. However, please be cautious that this needs to be modified in some cases, for example, in logistic regression, because the mu may have a different range as y does. So for logistic regression, we require the mean to be between 0 and 1, but not equal to 0 or 1. So in that case, you cannot directly use y, you have to use some perturbation. Then given mu 0, we can have the linear predictor eta 0 by the systematic structure. Of course, this is applied to every I. And then we can have our working dependent variable, or let's look at this one. For each zi0, we write as zeta I0 plus this term, the Taylor expansion term. So yi minus mu I0 times g prime mu I0, getting our working dependent variables. And finally, we need weights. So the weights by our definition is the variance of yi times g prime and mu I0 squared. Please note that since the variance involves parameters, we need to also put 0 here too, because the variance itself will be updated as our parameter value changes. So in the update step, we first run weighted least square using the weight matrix and the working dependent variable. Given the new beta value, we update eta as the linear predictor. And given the eta, we update mu I based on the inverse of the link function. Previously, we have eta I equals g mu I. Now we write mu I equals g inverse eta I. And finally, given these new sets of values, I can update my working dependent variable again using eta I1 and mu I1. And I can also update my weights again using the new variance based on the new parameters and also mu I1. So I have the zi1 and mu I1. Then I repeat the update again and again until convergence. So here the convergence is usually determined by the beta. So if the beta vector, the p-dimensional beta vector, stay pretty stable after iteration, so after from k, say k to k plus 1, if it doesn't change much, then we will call the algorithm as converge and we stop the iteration and we report the converged beta value as our estimate as our MLE estimate of beta. Okay, so that's the general IRLS algorithm. For a specific application to logistic regression, we consider two cases for logistic regression as we did before. The case one is for individual data. For individual data, yi is equal to 0 or 1, and each i's covariant vector or feature values are all different. Otherwise, we're going to combine these two observations into one observation, which is what we call group data, because we don't want our design matrix to have repetitive rows. So in this logistic regression, we still follow that general IRLS, but we will concretize what is the G function, what is the variance of Y. So please note that in IRLS, we do need those things. Okay, let me summarize. First is we need our data, that's Y and our design matrix X. Second, we need the link function G. And third, we need the variance formula for Y, variance YI. And that depends on our model specification. So G is from systematic structure, variance of YI is from the random structure. So now, in the logistic regression, we write mu I always as expectation of yi. That's our definition of mu I. In this case, it's equal to the success probability parameter called pi I. And variance of yi by the Bernoulli random structure is pi I times 1 minus pi I. And then we have the length function eta I equals to logit yi, which is defined as log pi I over 1 minus pi I. So we can write this just as a G function of pi I. Here, pi I and mu I are the same thing. So we just, whenever we write mu I, we can write pi I. But the reason we still keep two notations, mu I and pi I, is because for group data, mu I is not equal to pi I anymore. So with this G, we take differentiation, and we have 1 over pi I plus 1 over 1 minus pi I. This is because we can write this log ratio as log pi I minus log 1 minus pi I. And combining them, I get 1 over pi I times 1 minus pi I. Then I start my iteration. So in the kth iteration of IRLS, so the working dependent variable zik is equal to eta ik plus yi minus, it used to be mu I, but here we're pi ik, times it used to be g prime mu I k. So because g prime takes this form, I just put it here. So I get 1 over pi ik times 1 minus pi ik. For the working dependent, for the weight wik, so I need the variance in the kth iteration, and the variance is pi I times 1 minus pi I. So I use the kth value here, and I also put the g prime square here. Okay, so you see I have some cancellation. Pi ik times 1 minus pi ik appear both here and here. I cancel out one copy in the square, and I take the inverse and the inverse again. So this gave me wik as pi ik times 1 minus pi ik. So with the working dependent variables and with the weights, I can run weighted least squares. That will give me the next set of value for beta. I call beta k plus 1. And with this, I just get a linear predictor, updated eta, and then finally, I will get the new set of means, pi ik plus 1, by the inverse of the eta ik plus 1. And specifically for logistic regression, the inverse of the logit link function is the exponential times 1 plus exponential. So here will be exponential eta ik plus 1 divided by 1 plus exponential eta ik plus 1. So one special thing we need to note for logistic regression of individual data is that here we cannot directly use yi as pi I initial values. The reason is pi I is 1 or 0. But if you look at this formula, if pi I is 1 or 0, we will have a dividing 0 issue. So we cannot get yi to be exactly 1 or 0. We need to perturb it. So a simple perturbation is to add a small constant when y is 0, or minus a small constant when y is 1 as our initial values for pi I. So this is also related to a common issue we have for logistic regression when our data, the features, or the two classes can be perfectly separated by features. So here I'm just making up one example with only two predictors. Here x1 and x2 stands for the two predictor values. And we actually have data points marked as zeros here, ones here. You see that these two sets of observations can be perfectly separated by multiple lines. Each corresponds to a linear predictor in our logistic regression. So what this suggests is that you really do not have an MLE to be obtained, because whenever you have this perfect separation, after some iteration, you will have for some data points to have pi ik value to be exactly 1 or exactly 0. Then you are going to have this likelihood function basically exploding. So you cannot really maximize an infinite likelihood function. So that's why in R, if your data are perfect separated, you'll get a warning message saying that the algorithm doesn't converge. So this is the motivation of support vector machine, which means that out of those all possible lines for perfect separation, you will find one that gives you the best support. So that's why SVM is very popular for this kind of case. And that's the motivation of getting support vectors. And coming back to our main theme, now let's move on to case 2, group data. So for group data, we mean that we have multiple observations that share the same covariates. So then we put them into one group. And we use the number of observations in group I as Ni notation. And these points, those observations, they share the same row in the design matrix as Si transpose. Then for group data, our random structure become Yi follows binomial with total Ni and success probability pi I. Again, we have the parameters for the model we need for IRLS. So mu I is still the expectation of Yi, but here is Ni times pi I, not just pi I. The variance of Yi comes from binomial is Ni times pi I times 1 minus pi I. Now we want to write it in terms of mu I. So we get mu I times Ni minus mu I divided by Ni. And eta I is the link function on Yi. So we know that in the logistic regression, it's always log pi I over 1 minus pi I. We want to write this in mu I. So we have mu I time divided by Ni minus mu I. And we call this the g function of mu I, the link function. And then g prime mu I is, of course, we have log mu I differentiation 1 over mu I, and log Ni minus mu I is derivative should be negative 1 over Ni minus mu I. That because we have a negative log. So those two negative signs cancel. We have this plus. So combining them, we have Ni over mu I times Ni minus mu I. These are all the things we need to start the iteration. In the kth iteration, we still use that formula for working dependent variable. So we can get zik equals eta ik plus yi minus mu ik times this is g prime mu I at the current value. For the weights, it's still this formula. We need the variance of yi at the current values and also the square of the g prime mu ik. So we see the variances of this form, and the g prime mu I is directly its inverse. So when we multiply them, they get canceled. So we're only left with g prime mu ik in the denominator. I will take its inverse. So that will give me mu ik times Ni minus mu ik divided by Ni. Okay, so with the working dependent variable and with the weights, we are now finally be able to update our parameters. So what we're going to do is we're going to repeat what we did for the individual data. So this update based on weighted least square still applies, and this linear predictor update still applies, and the calculation for pi I still applies. So we're going to call these 3 steps star. So the same star is going to be used. And finally, given the updated values of pi i's, we are going to update mu I. And this is easy because mu I is just equal to n. This is easy because mu I is just equal to Ni times pi I. Okay, that's for group data. Same as for individual data, we need to make sure that our initial values of mu I are not exactly 0 or Ni, but somewhere in middle. Otherwise, we will have dividing 0 issue. All right, so these are the specific application of IRLS to our logistic regression. We can see that we are doing this reweighting and reweighted least square constantly in this application. Next, we'll talk about the goodness of fit of a GLM to our data. To achieve that, we are going to compare the likelihood fitted by GLM, the likelihood of GLM versus the likelihood of a saturated model, where we give each observation yi its own mean parameter mu I, and those mu1 to mu n are not connected anyway. In other words, we can have n parameters that can vary freely. So we can call this degree of freedom as n. In contrast, in the GLM, we are going to have this systematic structure that link all our mu1 to mu n into this common beta. This beta is only p-dimensional and p is less than n. So therefore, the degree of freedom for GLM is p instead of n. So we want to know whether this less complex, simpler model GLM can fit our data similar to what we can achieve with the saturated model. So in order to use this likelihood ratio statistic idea, we are going to compare the maximum log likelihood of GLM versus the maximum likelihood of saturated model. So therefore, for this maximum likelihood, what we taught about the IRLS algorithm is necessary to find the MLE estimates of GLM parameters for beta. Therefore, we can have the corresponding MLE estimates from mu1 to mu m. So for this log likelihood ratio, we have -2 log likelihood ratio. And we can actually write the log likelihood. So therefore, we have 2 times the log likelihood of the saturated model, MLE, minus the log likelihood of the GLM MLE. This formula applies in general to all our GLMs. Now, specific to our logistic regression model with group data, we can actually use this form, which we derived before. So if you recall in our lecture 8, I think, we had derived the log likelihood of logistic regression for individual data. That looking at this form, essentially based on the Bernoulli distribution for the probability mass function, which we used for the likelihood, we can write the log likelihood as summation over data points, yi times log yi pi I, plus 1 minus yi times log 1 minus pi I. For group data, yi will stay as yi, pi I will be changed to mu I. Okay, so we're, pi I is going to, sorry, my bad. Pi is going to stay as pi I, but this is going to be changed to ni minus mu I, because we are going to have that. And also, if we are going to write it in terms of mu I, we are also need to worry about that constant ni here. So in other words, we can derive a similar log likelihood. So based on the probability mass function for binomial instead of Bernoulli. So we are going to have this as ni choose yi times pi I to the power yi times m times 1 minus pi I to the power ni minus yi. But that combinatorics number can go away because it has nothing to do with pi I. So therefore, we're going to stay with this formula, but we're going to change this 1 to ni. Okay, so then we're going to write yi in terms of mu I. So that's actually mu I divided by ni. So then we can actually put that formula into here. So that's what we have for the log likelihood of the group data. And this is what we have for saturated model, because in saturated model, the MLE for each mu I is just yi. So we use yi as the mu I hat saturated. And for the GLM, we're going to obtain the mu I hat from this relationship. So given the beta hat, we can use this inverse of the length function, inverse of the logic function to obtain pi I hat, and multiply pi I hat by ni, we get our mu I hat. So this is what we have from the GLM. And therefore, combining the common terms, we get this term, right? Yi times log yi over mu I hat, ni minus yi times log ni minus y over ni minus mu I hat. And we give this -2 log likelihood ratio a name deviance. Deviance is a very useful term to know because we use deviance for assessing the goodness of fit of any GLM. And this deviance, based on the asymptotic theory of this -2 log likelihood ratio, follows a chi-square distribution with n minus p degrees of freedom. This is exactly the difference of degrees of freedom between the two models, n and p here. But for asymptotics to work, we actually need to have, for each group, the sample size within the group, ni, must go to infinity, not just n go to infinity. The reason we need this is because here for each parameter, for the saturated model, we would have ni observations to estimate it. So for this estimation, for the saturated model MLE, we need to have a large sample size. If we are under the individual data scenario where we only have one observation in each group, that is ni equals 1, then we do not satisfy this asymptotic condition. So then this chi-square asymptotic distribution cannot be used. So this asymptotic distribution, whenever it's applicable, it's very useful in the case that it can help us assess whether our deviance statistic we calculate on our data is big enough. So when it's big, it means that it's unlikely to be from this null distribution. So which suggests that here the null is the GLM does not differ from the saturated model in terms of explaining data. So under that null, if we have the D to be too large, that's an unlikely or rare event. Then retrospectively, we can say, okay, given this large D, we have a strong evidence against our null. Then we will reject the null. And by rejecting the null, we are saying, okay, the GLM does not fit as well as the saturated model, considering the difference in the degrees of freedom. Therefore, we conclude that GLM fit our data poorly. So in other words, if you want to see whether your model fit your data well, you want to have a small d, a small deviance, so that it suggests GLM is doing a very reasonable job compared to saturated model. Therefore, we think GLM fit our data very well. Because the saturated model clearly fits our data very well. We're just use the data as our model parameter estimates. Okay, so this is the general way of assessing goodness of fit. The second way is to use what we call the Pearson's chi-square statistic. So this one is not based on the likelihood theory. And so therefore, nowadays, whenever we can use the deviance, we prefer to use the deviance. However, the Pearson's chi-square statistic has a very interesting historic root. So if some of you have ever heard of the Fisher's exact test, for testing whether two variables have independence given a count or contingency table like this. So let's say variable 1 has 2 values, variable 2 has 2 values. We can summarize our observations into a count matrix. Let's say we have count A observations with values A for both variables, and we have B observations with value 2 for both variables. So given this count matrix, we can summarize the marginal counts for variable 1 as A plus B for value A, C plus D for value 2. For variable 2, we can summarize the marginal total as A plus C for variable 1, B plus C for variable 2. And the total, that is A plus B plus C plus D, is set to n. So therefore, if we are assuming these two variables are independent, we can compute the expectation of this count A, which should be n times the marginal probability for variable 2, A plus C over n, times the marginal probability of variable 1 for taking value 1, A plus B over n. So when they are independent, their joint probability is just the product of their marginal probability. This will be, and this joint probability times n is what we expect for this count. So although Fisher's exact test uses the hypergeometric distribution to calculate the p-value for this observed data, but we can also use Pearson's chi-square statistic in this way. So basically, we're going to have an observed count as our data. We're going to calculate the expected count based on this independence assumption. And we're going to assess the difference between observed count and expected count. That gives us the Pearson's chi-square statistic. So it's defined as a summation over the categories we have here. And for each category K, we get its observed value minus our expected value under our model assumption, take the difference, square it, and we also divide this difference by the expected count as kind of a normalization. So if we apply the Pearson's chi-square statistic to our group logistic regression case, this is what we get. So a very interesting thing is that we're taking a summation over our groups, but within our group, within each group I, we have two sub cases. One is when the number of observations that are equal to 1. The other is the number of observations that are equal to 0.
So that is equal, this number is Ni minus Yi, right? So Yi is the observed count for ones, and Ni minus Y is the observed count for zeros. And mu I hat and n minus mu I hat are the expected values we calculated from GLM. And then the expected is divided here and here, and we take the sum. So by some algebra combination, this is what we get. And asymptotically, this Pearson chi-square statistic under the null hypothesis that the GLM is just the model where our data are generated from, we can have the chi-square asymptotic distribution with the same n minus 2 degrees of freedom. So even though Pearson chi-square statistic and the deviance have different forms and different values on a particular data set, they are asymptotically following the same chi-square distribution. So I would say whenever we can use the deviance statistic, we will use that for assessing the goodness of fit for our model. But the Pearson chi-square statistic is also good to know. So in our next lecture, I will talk about the inference of beta in GLM based on the MLE beta hat we obtained from the IRLS algorithm. So please note that even though we are doing hypothesis testing under both goodness of fit and inference of beta, but they're actually for different purposes. So for goodness of fit statistic or test, we try to assess whether the model we propose is likely a generative model from which our data are generated. So here, the null hypothesis is that the GLM is the generative model, or it is actually very similar to what we call the saturated model. So we are comparing the GLM versus saturated model and set them to be equal under the null hypothesis. But for the inference of beta, and also, sorry, and we want to be able to not reject the null for goodness of fit, because not rejecting the null means that we accept the GLM. We do not reject that GLM is the generative model, so we are happy with the model fitting, in other words. But for the inference of beta, we are interested in whether the beta is equal to 0 for some of its elements. So that's what we did for the wall test, likelihood ratio test, and hierarchical ANOVA in the linear model. So next, we're going to do something similar for the GLM. And for the inference of beta, what you really want is to be able to reject the null so that we can claim that some predictors do have an effect on the response, they shouldn't be removed. So we have different expectations for behind our analysis when we use goodness of fit test or the inference of beta test, like the wall test and the likelihood ratio test for that. Okay, so that's a very quick recap or re-recording of the lecture 10. So I will also post a very interesting PDF to RCSLE, which was suggested by one of my students, Guang Ao. It's actually about a lot of very important tricks for matrix calculations. It's called a matrix cookbook. So I'll post that to CSLE for your reference. Thank you.